Hello, and welcome to another video demonstration of SIMWISE 4D. In this example, we'll look at how to set up and perform a durability analysis to calculate the life expectancy of an arm component that is part of a subway door opener mechanism. Here we are inside the SIMWISE model of a subway door opener mechanism. For this example, we're going to be performing a durability calculation on this arm right here. This arm is attached to a sample door. If we look at the material properties for the door, we can see that we have a mass specified of 200 pounds. We also have friction applied to the sliding joint for the door to represent some resistance that might occur due to various rollers and dirt in the trackway and things of that nature. If we play the animation here that's already been run, we can see we have the simple motion of the mechanism. What we're going to do is we're going to include this arm right here in the FEA analysis now. So if we right click on it, we can choose Include in FEA. The first thing we'll notice is these icons, or these graphical icons that have showed up. These icons represent the forces that are calculated from this joint. They represent the forces being placed on this face right here. We're going to change that in just a moment. But the idea here is that we're telling SIMWISE onto which faces it's going to bear the calculated loads for the joints. So what we need to do for this here is simply right click on the load graphic and choose Distribute on Face, and then we can specify a new face, and we'll select this inner diameter. Notice how we have another graphic that's still showing out here. That graphic belongs to the other constraint that's connected on this end. Let's go ahead and let's hide the door for simplicity here. And we can see this graphic right here. Notice when we hover over the graphic, the constraint that's associated with the graphic will highlight. So if we hover over the graphic here, notice the fixed joint at the upper end of the arm. Go ahead and right click on it, choose Distribute on Face, just like we did for the first one. Select the inside diameter. Now we'll modify the material properties for the arm. Right click on the arm, choose Properties, and if not already selected, click on the Material tab. Click on Change, and then next to the Material field, click on the drop down button and change the material to Steel ANSI C1020. It's important to note here that we're using a material that has durability properties defined to demonstrate this. If we click on Edit the Database, we can click on Advanced, and we can see a more comprehensive list of the materials and their properties. For this particular material, we can see that we have durability variables defined for it, or durability properties. In the future release, it's more than likely that this dialog box interface will not be used. We'll click on OK, click on Close. We'll go ahead and we'll right click on the door panel in the browser here and click on Show. And then we'll click on the simulation settings icon, and we'll change the animation frame rate to 0.01 to create a finer resolution of our stress results. We'll click on simulation settings, and we'll define a stop control that stops the simulation just after time reaches 2 seconds. Now we're ready to run the analysis. We'll come down to the panel here and we'll click on the Motion with FEA option, and then we'll click on Run. Here we could see a simultaneous motion and stress analysis being done at every single time step. So we're back after running the simulation, and if we click on the playback slider button here and we drag this through, we can see the entire range of motion and the stress resulting on the arm. This particular simulation took about 4 minutes using the time step that we specified. So now with the stresses available through the entire range of motion, we can right click on the arm, choose Insert Meter, and then click on FEA Result. This creates the von Mises stress plot through that range of motion. Now that we have stress results, we can go ahead and run a durability analysis. But before we run the durability analysis, we'll click on the SIMWISE settings icon. In the SIMWISE settings dialog, we'll click on durability, and here we can specify the type of failure criterion and different options to use for the durability calculations. Since we're looking at a problem here that has a relatively low stress in comparison to the yield, we'll look at a high cycle fatigue situation. Therefore, we'll use the stress life criterion. We'll use a Manson-Coffin method based off of the von Mises stress. And then, since we have a non-zero average stress for this loading, we'll use a Goodman correction. Next, if we look at the input settings, we can specify a certain range of frames to use for the calculations, or we can use the entire range of frames. Since we've simulated for one complete full cycle of the opening and closing of the mechanism, we'll go ahead and use the entire range of frames. Next, under fatigue factors, we can specify the different factors that will also affect the life of the product in terms of surface finish, any existing notches in geometry, and things of that nature. For this example, we'll define a notch factor of 1.3, and we'll define the surface factor based on a forged part. Next, under other factors, we have the option to specify some settings here that control the accuracy of our solution, and we can also control some of the settings used in the rain flow counting method. For this example, we'll leave these at the default values. Now that we've set some of these parameters, we'll click on Close, and we're ready to run the durability analysis. We'll simply come down here to the panel, and we'll click on the Durability Solve button. The simulation runs fairly quickly, and then we're presented with a life plot of the life of this component based on our different factors. So we can see that we have roughly 3.3 million cycles that are expected until this part is expected to fail. This concludes this demonstration of SIMWISE 4D.